Today we're going to talk about one of the most important algorithms ever. It's used everywhere in wireless communication, GPS, image processing, signal processing. Like, for example, I'm talking right now into the microphone, then this audio information is processed and then sent to your computer via internet. When you process this audio, you use fast Fourier transform. But don't be scared. This sounds very complicated, but we're not going to talk about that today. Everything we're interested in here today is just competitive programming, right? And, right. So there's the question, whether recording? Yes, so there will be a recording available on this YouTube channel. I will be also writing some notes, right, during this lecture. The link to the notes will also be available. And in the video description right now, you can already see like some materials that I used to prepare this lecture, some articles, some videos. Also, there is a link to a contest where you can, where I added a bunch of problems and I would recommend solving them. It's very important to solve problems, not to just listen to a lecture. During the lecture, I will only answer the questions from the chat that are relevant to what I'm talking about right now. So if you have a general question, then you can ask them at the end so that we have some kind of a clean recording, right? So that people can watch afterwards. I think that's everything that I have to say. You're not allowed to enter the contest. Okay, I see. Right, so you probably need to first enter the group before the contest. That's my bad. Right. I will fix it now. So now there are going to be two links. First, you enter the contest, enter the group, and then you enter the contest. Right. So if you're watching this as a recording and you see that this video is pretty long, don't be scared. It's not because we cover too much or because the topic is too complicated. We're just going to take it slow. We aren't going to rush, and we'll try to do it step by step so that everything is clear. Let's start by talking about numbers. So for example, you have two numbers, 123 and 642. You want to add them up, right? So how would you do that? Normally we write them one on top of each other, and then we add them up digit by digit, right? So 3 plus 2 is 5, this is 6, this is 7. Sometimes, for example, if this would be 7, we would get 11, so we write 1 and carry the 1 here, right? This is how we add numbers. Adding numbers is pretty easy. On the other hand, if we would try to multiply these two numbers, we do it in a pretty similar fashion. We write them one on top of each other. And then we take the first digit and multiply by this number, right? So we get 2, 4, 6. Then we get, oh, it's hard. 2, carry the 1, 9, 4. And then we multiply it by 6, 9, 2, 7. And then we add all this up. It doesn't matter if I made a mistake. So it's 0, 8, 7. I'm not sure if that's correct. That's not that important. But you can see that for some reason multiplying numbers is so much more complicated than adding numbers, right? If we think about it from our computer science perspective, right, 6 by 3, okay, yeah. Okay, anyway, doesn't matter, sure, I made a mistake, that's okay. That kind of proves my point, right? So multiplying for some reason is so much more complicated than adding up, right? We have kind of linear number of operations to add two numbers up in terms of the length of the number, right? If you have two numbers of length n, and we try to add them up, this takes all of n time. We just add the digits and then maybe do some carrying. Carrying is easy. But when you do multiplication, you actually do a quadratic number of operations, right? Because you take every digit of the second number and multiply it by the whole first number, right? So basically, you multiply every digit with every digit. That's a lot of work. And we would like to understand why. Like, is there anything fundamentally harder about multiplication compared to addition? So I hope that everybody knows this method of multiplication. All right, yeah, so everybody knows this method of multiplication, where this is sometimes called long multiplication. There are other ways to multiply numbers. I guess this is the most popular, but basically all of them take this quadratic time. And some variations of this specific algorithm have existed for 4,000 years. So it kind of feels like it would be natural that there is some fundamental barrier why we can't do better. And basically what we're going to try to answer today is, can we? Maybe we can. So now we're moving back to the future from 4,000 years ago to approximately 65 years ago. So it's 1960, Soviet Union, Moscow. Famous mathematician Andrei Kolmogorov holds a seminar to resolve some open problems. One of the problems was exactly number multiplication. So Kolmogorov conjectured that doing this long multiplication is basically optimal. So he wanted to prove that doing better than n squared is impossible. Why did he conjecture that? Well, because of the same reason as what I just said, right? People knew how to do it for 4,000 years. Nobody came up with a better way. Well, probably there is some natural barrier. They hold this seminar. There were other problems. And then a week later, a 23-year-old PhD student called Anatoly Karatsuba came back and showed an algorithm that actually works faster than n squared. His algorithm was in a very weird time complexity. Maybe you've seen this algorithm, the known Karatsuba algorithm. It works in time n to the log based 2, 3. That's a very weird time complexity, but basically it's approximately n squared of n, a little bit more than that. So the conjecture was actually false. Actually, Karatsuba also proved one other problem from this seminar, but that's not relevant for us. And this algorithm is actually pretty simple. It's kind of surprising that nobody thought about it before. If you want, you can learn about it online. I don't think it's going to take too much of your time. It's just basically divide and conquer. But we're not going to talk about it today, because we're going to solve this problem even faster. We're going to solve it almost as fast as we do addition, right? So addition we solve in linear time, and this problem we're going to solve in time of n log n. Almost linear, right? Okay. So this was some history. Now let's start solving the actual problem. The actual problem we're going to be solving is a little bit different. It's not number multiplication, but rather polynomial multiplication. So, for example, imagine that you have a polynomial x squared plus 2x plus 3, and you want to multiply it. Okay, this is a bad sign for multiplication. Multiply it by 6x squared plus 4x plus 2. Right? I want to say that polynomials and numbers are pretty similar to each other. Because to multiply polynomials, you can also kind of just use this long multiplication, right? Let's write it like this. So we have x squared plus 2x plus 3 times 6x squared plus 4x plus 2. We first multiply by 2 everything, right? We get 2x squared plus 4x plus 6. Then we multiply by 4x. We shift it because now it's like times x more compared to multiplying by 2, right? We write 12x squared here, 8x here, 12x here, 8x squared here, 4x cubed here, and so on. And then we add these things up, right? We write all common summands on top of each other, and then we sum up, for example, 2x squared plus 8x squared is 10x squared. This is exactly the same thing you do when you multiply numbers. Why is it the case? Well, because if you have a number, 1 to 3, it's just basically 1 times 10 squared plus 2 times 10 plus 3. It's the same as this polynomial, but instead of x, you have 10. So basically, when you have a number, you just substitute, like the digits of a number are basically just the coefficients of a polynomial, and then you just put 10 instead of x. So these problems are actually very close to each other, and specifically we're going to talk about polynomial multiplication. If you want to multiply numbers, you just think about the digits as coefficients, multiply the polynomials, and then you just need to do the carrying, right? Exactly the same way as we did here when we multiplied numbers, right? We need to sum up all these digits, but then we still need to carry to the next digits, right? Okay, so we're gonna solve polynomial multiplication. That's basically the only thing you need to know in advance to understand this lecture. I hope this makes sense, how to multiply polynomials. Normally you don't do it like this. You just take these two brackets and then you multiply every element on the left with every element on the right, and then combine things that have the same power of x, right? If you know this, you're good to go. Maybe it's a good idea to know what a sine is and what a cosine is, but that's not that important. We're not going to use it that much. If you don't know it anyway, I'm going to explain what it is. But remember that even though I'm saying that you don't need to know much to understand what's going on, it doesn't mean that it's a good idea to necessarily learn this algorithm if you're a beginner. Because even if you understand the algorithm itself, the problems that this algorithm uses are normally hard. Even if you already have your fast Fourier transform written, solving the problem with it is already a hard task. So if you're a beginner, it kind of doesn't really make sense to learn this, because anyway, you're not going to be able to use it maybe. So I would say that this lecture is for Codeforces experts and above, so like 1700 and higher. But if you're just interested, obviously you can listen. That's okay. Everybody's welcome. So I remember the first couple of times I've attended a lecture and on fast Fourier transform, I was completely frustrated because there is a lot of math, very complicated steps. It's very hard to follow what's going on, and I have no idea how to remember all this stuff. So I'm given a bunch of formulas, they don't make any sense, and I'm somehow supposed to remember what all this does. It's hard. And also there are some matrices, vectors. I don't know what a matrix is. That's too complicated. So in this lecture, we'll try to solve the problem with just simple techniques. We'll ask the right questions. We'll look for the simplest answers to these questions. And my goal at the end is that when you finish listening to the lecture, you don't need to remember anything. You can just understand the concept, and then if you need the algorithm, you can just recreate the steps that we did. And when you will be actually solving your first problem, I would suggest that please don't use my notes, my code, or whatever you've written down on your piece of paper, try to actually think from an empty sheet of paper. Try to come up with the algorithm again and fix the bugs and everything like that. And I think that's a very important part of learning, and this will help you a lot. Okay, so what problem we're solving, right? We're solving polynomial multiplication. How do we encode polynomials in our computer, right? We have a polynomial p of x, which is equal to p0 plus p1x plus p2x squared plus p3x cubed, and so on, plus pn minus 1 x to the power of n minus 1. If you're doing math, sometimes the last power is assumed to be n, but we're computer scientists, right? So we have an array of size n, and then its indices are from 0 to n minus 1. And it's easy to represent this polynomial, right? We just have a vector or array or whatever, which is like p0, p1, p2, and so on, pn minus 1. And as I said, with numbers, the same thing applies here. If you want to sum them up, it's very easy, right? You have two polynomials. You just sum up their coefficients, p0 plus q0, p1 plus q1, and so on. This takes linear time. But if you want to multiply them, that's much complicated. So let's remember how it works if we want to multiply two polynomials. We take this polynomial, and we have another, just with q, and we need to multiply every summand in this sum with every summand in the second sum, right? So we have q0 plus q1 x, and so on, plus qn minus 1 x to the power of n minus 1. And when we have two summands, we have like something like pi times x to the I times qj times x to the j. Our powers sum up, so we get pi times qj times x to the power of I plus j. And let's do this for every pair, right? If we try to understand how this formula works, then we get some polynomial r. Our polynomial r is just the product of polynomial p and polynomial q. And what will be the coefficients of this polynomial? So the coefficient k will be just sum over all pairs, pi and qj, such that they add up to k, right? So this power now is k, and we want all pairs I and j such that they sum up to k. So what these would be? So it would be p0 times qk, right? 0 plus k is k. p1 times qk minus 1. p2 times qk minus 2, and so on, pk times q0. In other words, this is just sum for j from 0 to k, pj times qk minus j. I hope you're familiar with this, but we're just trying to remind ourselves of that, right? Or again, in other way, it's just sum over all pairs j and I and j, such that I plus j is equal to k, pi times qj, right? Okay, it's obvious how to solve this in n squared time. We just go through all pairs here, I and j, and add this to the corresponding I plus jth element on the outside. Let's actually write the code for this algorithm, right? So we want polynomial multiplication. I will be using C++. I hope you know it, because anyway, it's kind of hard to solve problems on FFT with Python, because normally they tend to be with high limitations and everything. So we have two polynomials, right? We have polynomial p and we have polynomial q. we create a polynomial R, and now let's think how many coefficients it should have, right? So P has some number of coefficients, Q has some number of coefficients. What would be the number of coefficients in R, right? So when we multiply polynomials, their degrees sum up, right? But if we're talking about the number of coefficients, let's think about it. So we have Pn minus 1 here, for example, m minus 1 here. So what is the largest sum that we can get? The largest sum would be n minus 1 plus m minus 1, which is n plus m minus 2, right? So the largest coefficient would be n plus m minus 2. But because they start from 0, right, from 0 to n plus m minus 2, in total there are n plus m minus 1 coefficient. So it's p size plus q size minus 1. Initially, we just set them to be zeros. And now we go through all pairs of coefficients in P and in Q. And we add their product to the resulting index in J, right? Pi times Qj. And at the end, we just return the answer, right? Return R. This obviously works in quadratic time, very simple. This is basically doing the long multiplication of numbers, just in a different way. Right, sorry about that. Plus equal, yeah, good catch. Great. But we want to be faster, right? This is very simple, but too slow. The question that can come up to your mind right now is, why do we even care? Actually, let me make my webcam a little bit smaller, so that you can see my whole screen. Why do we care? I don't remember a single problem when anybody would ask me to multiply polynomials. Maybe multiply numbers, but I don't remember the last time I had to multiply large numbers. Why would we ever care about something like that? Well, actually, what we care about is exactly this formula. This is the formula that we care about. Actually, normally in problems that involve fast Fourier transform, we don't have any kind of polynomials. We just reinterpret something as a polynomial. You just have two sequences, P and Q, and you want to get a sequence R that looks like this. A very natural question, why would you ever want a sequence that looks like that? But I just want to say that it's just an interesting observation that in many, many problems it appears. So let me give you an example. Imagine that you're solving knapsack without weights. So basically you just have some amount of gold, maybe. And there's another knapsack for silver. You're just trying to take as much gold and as much silver as you can within the limitations that you have. So you can't take more than, I don't know, S kilograms of gold or silver. And imagine that you already solved the knapsack, right? So you have these items, I don't know, x1, maybe x is not the right value, let's say a1, a2, and so on, an. And you solve the knapsack. So for every value from 0 to s, you know whether it's possible to obtain it or not. And with silver, you have the same thing, right? You have b1 and so on, bm. And for every value from 0 to s, you know whether you can get it as a sum of some of these elements or not. Or even you know the number of ways to do that, right? And now I tell you that actually you will have not two knapsacks, but only one knapsack. So you should put all your gold and all your silver into one knapsack. Maybe gold and silver was not the best idea because gold is more expensive, so maybe you want to take only gold, but in my imaginary situation, they are the same, right? We only care about weight. We don't care about what kind of things we're taking. So now we'll again want to know for every value from 0 to s whether it's possible to get like j amount of gold or silver, right? So imagine that you have this array. This array will be p0 and so on ps. That tells you, can I get this amount of gold or not? We'll get an array q0 and so on qs. That tells me, can I get this amount of silver or not? And now I'm asking for an array j, for an array r, which tells me, can I get this weight if I use both silver and gold? And if I have j amount of everything, it just means that the amount of gold I have and the amount of silver I have just sums up to j. So basically what I want is just a sum over all pairs of I and k, such that I plus k sum ups to j of I take I amount of gold and I take q amount of silver, and I take k amount of silver, right? And if either of these things, if both of these things are ones, right, so I can do that, then the answer should be 1. So here, I actually don't get whether I can or not, I somehow get the number of ways to do that, right? So if pi is 0, then the product is 0. If qk is 0, the product is 0. So if I can't get either I gold or k silver, then the answer is no. Otherwise, the answer is 1. And then I sum up all these ones. So I sum up the number of ways you can split j into gold and silver, right? And this is just one example. So basically, when you have two things and you want to somehow calculate, take all pairs and sum them up, then you get this convolution. And I don't remember if I said that. This sequence R is called a convolution of P and Q. And actually, normally, this is what we care about. We care about convolution. We don't care about polynomials. But it just turns out that convolution is just, if you reinterpret this sequence P as a polynomial, you reinterpret this sequence Q as a polynomial, and you multiply these polynomials, then the coefficients of the product is the sequence that is a convolution. But normally, when we're talking about polynomials, when we're talking about FFT, we don't really care about polynomials. We're solving some DP problem or something like that. Great. So there are a bunch of things one can do with polynomials, right? We already talked about summing up two polynomials. You can take R plus Q. You can do it in n time. As we talked about, R times Q is kind of complicated. We only know how to do that in R times Q. What are some other operations one could do with polynomials? Yes, so there's a question about silver and gold. Let's come back to it. So, as I said, we don't care about the value of silver and gold. We just want to take specifically J amount of everything, right? So some of it will be gold, some of it will be silver, and together it should be J. And we want to calculate for all possible values of J. Right, so as I said, we can sum up two polynomials, we can multiply polynomials. What other interesting operations there are with polynomials? I want to say that an interesting operation is evaluation. So we can take some polynomial R. Okay, R is a bad. Why did I write R? It should be P. P plus Q, P times Q, P of A. Right? How do you compute P of A? Well, you just substitute A for X, right? So you have P0 plus P1A plus P2A squared, and so on. And you can just calculate that, right? It's easy to do in linear time. That's great. Yeah, this is called evaluation. Because you take a polynomial, you take a point, and then you evaluate the polynomial in this point. No, convolution is a different operation that we talked about before. related to multiplication. But actually, I want to say that having the coefficients of a polynomial is not the only way you can represent a polynomial. Let's just think about what a polynomial is, other than just a sequence of its coefficients. I want to say that there are other ways to represent a polynomial, and we will think about 3 different ways to represent a polynomial. So we already know one, which is the list of coefficients. And I want to say that you can do better. You can do 2 other ways. Matrices sounds very complicated. We don't want anything complicated, right? So any other ideas? Okay. Let me give you a hint. So, for example, okay, great. I see the right answer. Roots, yes. So one of the things is roots. Maybe you know that there are roots of a polynomial, right? It's just some values a, such that if we evaluate the polynomial, then it becomes 0. And maybe you even know that every polynomial of degree n, or degree d, let's say, degree d, has at most d roots. And if a polynomial has a root, then it's actually divisible by x minus this root. So actually, p of x can be written as x minus a times some other polynomial. Right? And then if we substitute a for x, here will be a minus a, so it will be 0 multiplied by something. And, well, not always a polynomial has exactly n roots. It has at most n roots. Later, we'll actually learn that you can always think that it has n roots. But let's imagine that it has n roots. Then the polynomial can be written this way. It can be written just as a product of x minus the first root, x minus the second root, x minus the third root, and so on. And then maybe there is some number in front of it, right? Because this way you can only get a polynomial that has the largest coefficient 1, because you just multiply all x's together. If the largest coefficient is not 1, but maybe 2 or 3, you'll get some constant here. So for example, 3 times this product. Let's think about our operations, right? Multiplying polynomials, evaluating polynomials, adding up polynomials. If I want to evaluate, it's very easy. You just substitute here, you subtract, and then you continue multiplying, right? There's a linear number of operations you need to do, right? You just replace every x with the value that you want, right? You want to evaluate p of d, right? You substitute d for x everywhere and you compute that. Multiplying is also very easy, actually, because if you just store the roots, we know that our polynomial is just the product of such things. So, for example, p has roots a, b, c. P has these roots, q has roots d, e, f. How can I get the roots of their product? Well, for the product, it's either these roots or these roots, right? If I multiply, then it means that if p times q is equal to 0, then either p is 0 or q is 0. So the roots of their product is just a, b, c, d, e, f. But what about addition? Addition is actually kind of complicated. And I want to say that in general, it's basically impossible to do. So the problem with roots is that if you're given a polynomial in coefficient representation, the problem is that it's basically computationally impossible to find an exact algebraic formula for the roots of this polynomial. Why is it the case? Well, let's just think about simple polynomials. So what is the simplest polynomial? ax plus b is equal to 0. I think you know how to find the roots of this polynomial, right? X is equal to minus b over a. We just solve the equation. Then you have a quadratic equation. For this, you also have some complicated formula, right? Minus a plus minus square root of b squared minus 4ac over 2a. Then, if you have a cubic equation, there's also a formula. Maybe you don't know it. It's kind of complicated, but there is a formula, and it's called Cardano's method. Minus b. Yeah. Wow, crazy. Yes, indeed, minus b. I already forgot the formula. There's Cardano's method for cubic, and there's also Ferrari's method for, this is for degree 3, this is for degree 4. They are very complicated, but they exist, right? So it's possible to find an exact algebraic formula for roots of a polynomial of degree 3, 4, 3, 2, 1, and 0, of course. But if we consider a polynomial of degree 5, there is no formula. So it was proven a while ago that there is no algebraic formula for the roots of a polynomial of degree 5. Of course, in many situations you can just, basically in all situations you can approximate them. You can run some binary search, approximate where these roots are, something like that. But there's no exact formula. And why is it relevant here, right? I said, what if we want to add up two polynomials? If you add up two polynomials, then the degree of the sum has nothing to do with the degrees of the initial polynomials, basically. Oh, not the degree, the roots, right? The roots of the sum has nothing to do with the roots of the initial polynomial. So basically, you just need to calculate them from scratch. And this becomes almost an impossible task, right? So maybe talking about roots is not the optimal way to store a polynomial, right? I said that we're going to have three different ways to represent a polynomial, right? Coefficients, roots, and the third one. I think there was some comment. Yeah, set of points and values, which you can also call samples. So actually, a polynomial is nothing more than just a function, right? There are a bunch of different functions. I don't know, there is a function absolute value of y is equal to absolute value of x. Or there is a function y is equal to x squared. You can draw it like this. And a function is just defined by its values in all points, right? So we can just think about it as a collection of pairs like x and f of x for all possible values of x, right? And we can think about a polynomial in the same way. We can just think about, for every point, what is the value in this point? Well, sadly, that would be crazy. We can't store an infinite amount of information. But I want to say that for a polynomial, you don't need to store all the points. Actually, just a bunch of points is enough, if you know the degree of this polynomial. So imagine that you have a degree 0 polynomial. What is a degree 0 polynomial, right? You have p of x, and you don't even have the x, right? You only have the constant. So basically, p of x is equal to c. How this polynomial looks like as a function is just a horizontal line, right? If you know that the degree of this polynomial is 0, how many points do you need to know what this polynomial is? Actually, you need only 1 point. If I know the value of this polynomial for any input a, this is enough, right? The value is already the c. Maybe, probably, you also learned at some point how many points you need to represent a line. So if you have a line, how many points do you need to uniquely define the line, right? We know that there is exactly one line that goes through every 2 points. So actually, you just need 2 points, right? A line is just a linear function, so a polynomial of degree 1. What about a parabola? So a function, a polynomial of degree 2. Well, this is already beginning to be a little bit more complicated, but you can see the pattern. We actually need 3 points to uniquely define the parabola. We can go on. If you want a cubic functions look like this kind of, you just need 4 points. Any 4 points, it doesn't matter. You can choose any points. If you know the values in them, they uniquely define the polynomial. And you can see the pattern, right? Degree 0, 1 point, degree 1, 2 points, degree 3, 4 points. Yeah. So basically, if you have a polynomial p, you need its degree plus 1 points to uniquely define p. Why is it the case? Well, it's not hard to prove. Let's assume that it's not the case. So we have some points x1, x2, and so on xn, where n is degree of p plus 1. And we have p of x1, p of x2, and so on p of xn. And imagine that there is a completely different polynomial q, which also has degree at most n minus 1, which has exactly the same values in these points. So there are 2 polynomials that go through the same collection of n points on the surface, right? On the plane. So what can we do? Let's just consider a polynomial r, which is just p minus q. What can you say about r in these points x1, x2, and so on xn? What do you think? If p is equal to q in all these points, then if we subtract them, it would mean that r of all these points is just equal to 0. R of x2 is equal to 0, and so on. R of xn is equal to 0. So all these n numbers are roots of polynomial r. And we knew that p and q had degree at most n minus 1, then r also has degree at most n minus 1. But wait, that's weird. Didn't we talk about the fact that a polynomial of degree n minus 1 has at most n minus 1 roots? And this polynomial seems to have n roots, right? If you remember, when we talked about roots, we said that a polynomial is divisible by x minus a root for all its roots, so it can be written like that. If a polynomial of degree n minus 1 would have n roots, then there would be n things multiplied, and then its degree would be n. That's crazy. So actually it's impossible. The only polynomial of degree at most n minus 1 that can have n roots is just a 0 polynomial. So r is equal to 0, not as a value, but as a polynomial. And if r is equal to 0 as a polynomial, then it means that p is just equal to q in all points. So p and q are in the same polynomial. Great. So we learned that if we have a polynomial p, we can just consider any degree of p plus 1 points x and calculate the value in these points, right? We take any n points x1, x2, and xn. They just need to be distinct, right? Obviously, if you write the same point n times, this doesn't give you any information. And you just calculate the values of p in these points. These values uniquely define the polynomial p. And actually, there is a one-to-one correspondence. So not only there are no other polynomials p, but whatever values here I write, so I can just put any n number of any random points on a plane, and there exists a polynomial of degree at most n minus 1 that goes through them. So not only it's unique, but it also exists for any points. It's also possible to prove it. It's irrelevant for us. Just some trivia. Great. So this is a different representation of a polynomial, right? To represent a polynomial, we stored it before as just a sequence p0, p1, and so on, pn minus 1 of its coefficients. But you can also store it in a different way. You just store it x1, p of x1, x2, p of x2, and so on, xn, p of xn. If you have a polynomial of degree at most n minus 1, you just store n pairs, and this uniquely defines your polynomial. Remember, before we talked about a bunch of different yeah, it's kind of similar to the roots. I could also say that, yeah. So for the roots, when we store the roots, we basically store all the x's such that these values are 0. And here we store just any values. Yes, indeed, we can take any endpoints, x. If you remember, before we talked about 3 different operations: adding up polynomials, multiplying polynomials, and evaluating a polynomial in a point. What do you think about these operations if we store polynomials this way? If we store a polynomial as a collection of values, right? Well, if you want to add polynomials, it's easier, right? If you know the value of p in x1, you know the value of q in x1, right? Q of x1. You just sum the values, and then you get the sum of the polynomials, right? It's simple. Just remember that for that, we need these x values to be the same, right? If you evaluated p in points 1, 2, 3, 4, 5, and you evaluated q in points -1, -2, and so on, then you can't just sum them up. You need the same points, right? But if you have the same points, you can sum them up, no problem. Multiplying is also very simple, right? If you know the values of a polynomial, so for example, we know that p of x1 is equal to something, we know what q of x1 is equal to, then p times q of x1 is just p of x1 times q of x1. Yeah? Just remember that if we do that, the degree of a polynomial can increase, and then maybe it's not enough points anymore. So if we want to do that, we need to initially take maybe more points so that the resultant polynomial is still defined uniquely. But with evaluation, oh, this is kind of complicated, right? If we're asked to evaluate our polynomial in a point A where A is one of these n numbers, then it's simple. We already store this value. But if it's some different value, right? So you have a polynomial, you store only n points of this polynomial. If you want to know the value in some other point, well, it seems to be very complicated to calculate that. It's possible, but it's kind of hard. So let's look at some kind of table of everything that we talked about, right? So we have 3 different ways to represent a polynomial. We have the coefficients, we have the roots, and we have samples, right? We just take a bunch of points and consider this polynomial in these points. And we have 3 different tasks, right? Evaluation, addition, and multiplication, right? Let's remember, if we have coefficients, it's very easy to add. We just add in linear time. Okay, there's a question in the chat. You didn't understand addition with samples. So imagine you have just a function, f of x, and you have a function g of x. They're not necessarily even polynomials. Let's consider a function h, which is just f plus g. How to calculate h of x1? You just take f of x1 and you add g of x1. So if we have, for our polynomials, x1 p of x1, x2 p of x2, x3 p of x3, and the same for x2 q of x1, oh, x1, sorry, x1 q of x1, x2 q of x2, x3 q of x3, too many digits. Then if we want the product of these polynomials, right, r is equal to p times q, you just multiply the values in these points, right? R of x1 is just p of x1 times q of x1. So we have x1 and p of x1 times q of x1. x2, p of x2 times q of x2, and so on. You can do it in linear time. You just keep the x coordinates and multiply the y coordinates. Good. Graphically, it will be hard to do. Sorry. Okay, let's go back to our table. So if we have coefficients, it's easy to add. You just take the list of coefficients and other coefficients and add them up. Evaluation is also easy. You can do it in linear time. You just have the formula, you go through all the powers of x, and you substitute it for a power of that thing. Multiplication, as we said, is kind of complicated. We only know how to do it in n² time. Evaluation with roots. If you remember, we also have a formula, right? If you have roots, the polynomial is just x minus a times x minus 2 times so on. So we can just substitute and calculate. It also takes all of n time. Multiplication is also easy. If you remember, if we have roots of this polynomial, we just write them together, and now we have the roots of the product. And addition kind of takes infinite time, because I said that kind of it's impossible to do that. If you don't care about precision, like if you don't care about a specific algebraic formula, but just an approximation, it's possible, but then it's also kind of hard, because you have no idea how the root of a sum is connected to the roots of the initial polynomials. So that's not a really good representation. If you have samples, on the other hand, right, addition and multiplication is very easy. You just have the points, you have the values in them, you add these values, or you multiply these values. But if you want to evaluate, I said that it's hard, right? You know the values only in some points. How to get a value in some other point, that doesn't make sense. It's possible. You can do it in n² time. It's called, I mean, whatever. But anyway, it's anyway kind of slow. So you can see that no representation is kind of optimal. Every representation has some downsides. And what we will talk about is, well, coefficients are the most natural representation, right? And we kind of want to think about coefficients most of the time. But multiplication in coefficients is hard. But multiplication in samples is easy, right? So what do you think? What would we like to be able to do? To be able to multiply in the coefficients form. Right. We would like to mix them. So if there would be a tool, let me remove this. If there would be a tool that would allow us to jump from here to here, if there would be a tool that, given coefficients, P0, P0, P1, and so on, would give us the values in some points, x1, P of x1, x2, P of x2, and so on, fast, then we would be able to multiply polynomials in this way fast, and then we would like to be able to just go back. So we just need to have some kind of tool that, given coefficients, right? Let's draw it as a picture. So we have the world of coefficients. We have a polynomial P0 and so on, Pn minus 1. And we have the world of samples. x0, p of x0, x1, p of x1. And we would like to bridge these two worlds. And then if you can bridge these two worlds, then we would have a very simple algorithm. Simple algorithm for multiplication. And actually, from what I've already told you, how this step is called when we go from coefficients to values in points. Yes, this is called evaluation. Somebody's saying that it's easy. Well, it's easy if you have one point. But note that we need to evaluate in n different points. So evaluating in n different points separately would be still of n squared time, right? So for now, not that great. What about the other way around? If you have values in n points, you want to get the coefficients. How this operation is called? Maybe some of you know. I think this word appeared in the chat sometime before. So actually this is called interpolation, yes. And who would like to do these two operations? If we can do these two operations, I hope you believe that we can multiply polynomials. You just evaluate, multiply, interpolate. So let's actually write this kind of algorithm scheme, right? So we want, why did I call this FFT? This is polynomial multiplication, right? Let's find another algorithm, multiply 2, that will multiply polynomials. So we get a polynomial p, we get a polynomial q, and we want to find their product. So first, we want to evaluate p in some points. I don't know. Evaluate of p. Then we take and evaluate q. Note that these should be the same points where we evaluate, right? These are the values. And the points, let's say that the points are just numbers. We can choose with them however we want. For example, x1 is equal to 1, x2 is equal to 2, and so on. We'll just evaluate in points 1, 2, 3, 4, 5 for now. Then we want to multiply polynomials in the sample, in this sample world. It's very easy. You just go through all the indices and you multiply value by value. So you multiply in point 2, you know the value of p, you know the value of q, you just multiply them together. So you multiply p by q, and then you return the interpolation. Or maybe let's call it in a different way. This is a bit confusing, I guess. Let's say that r val is equal to p val times q val. And then interpolate. Everything outside of these formulas, or sort of these functions, evaluate and interpolate, works in linear time. So the only thing that is left is to do these two things. As I said, we need to be careful, right? Because to interpolate, r val should contain the number of points. This number of points should be enough to reconstruct the polynomial. So actually already here, when we evaluate, we should give some kind of hint how many points we want to evaluate in. And this should be, n should be equal to p size plus q size minus 1, as I said already, right? So the size of the polynomial r is the sum of sizes of p and q minus 1. Or in other words, the degree of r is the degree of p plus degree of q. But because we're not talking about degrees, but about the number of degrees, one smaller than the size. And we should evaluate in n points, right? For this to work. Okay. And here our val is of size n, basically. Okay, great. So everything that is left is just to understand how to evaluate in n-log time and how to interpolate in n-log time. Evaluation seems a little bit easier, right? Because, well, you just have the coefficients. We already can do it in quadratic time, right? You have a formula, right? P0 plus P1 times x plus P2 times x squared plus so on. You just go through this formula and calculate all these values, sum them up. If you do it n times for n different points, it would be n squared time. For interpolation, it's not even clear right now how to do it in quadratic time, but it's possible. But we don't want to do it in quadratic time. We want to do it in n-log. Okay. So once again, let me draw a scheme, and then we'll start understanding how to do all this stuff. Again, let me repeat that we don't know how to do evaluation or interpolation yet. I didn't explain that yet. That will be the rest of what I'm going to talk about. So we have P. It has coefficients, P0, P1, and so on, P minus 1. And we add zeros here so that there is enough coefficients for the remaining polynomial. Now we want to somehow transform it into the values, right? P of x1, P of x2, and so on, P of xn. We'll do the same with Q. We have Q0, Q1, and so on, Qm minus 1. Here we also add zeros so that we have a sufficient degree at the end. We evaluate Q of x1, Q of x2, and so on, Q of xn. And now we can just multiply them as numbers, right? We just write R of xj is just P of xj times Q of xj. And now we have the values of the product, x1 and so on, R of xn. And now we just want to go back. We want to have the coefficients of R. And this step is evaluation, and it will be called fast Fourier transform. This is the same step. We don't need two different algorithms. We'll just do the same thing with Q. And this will be called the inverse FFT, right? So FFT goes from coefficients to values, and inverse FFT goes from values to coefficients. Great. It's been already an hour. Sorry for being so slow, but I'm just trying to not rush. Okay. Normally at this point in time, a bunch of different matrices, formulas, and so on is being thrown at you. Let's try to avoid that as much as possible. Let's try to make it as simple as possible. Let's remember this scheme, right? We had coefficients. We convert them into values. We multiplied values just stupidly, right, in linear time. And then we convert back from values to coefficients. So the main idea that we're going to use is that we can choose any points we want, right? Here, we chose to calculate the polynomial, as I said, in points 1, 2, 3, 4, 5, and so on. But that's maybe not optimal, right? We want to choose the points such that it's as easy as possible to evaluate our polynomial in these points. What do you know? What kind of simple points to evaluate a polynomial there are? I want to say that it's easy to calculate a polynomial in 0. Because P of 0 is just P0. Because P1 is multiplied by x, which is 0. P2 is multiplied by x squared. It's also 0, and so on. P of 1 is also kind of simple, right? Because it's just the sum of all coefficients. because 1 to any power is 1. But this is not, like, it will not lead anywhere, right? Because now we're just trying to make some constant optimizations, right? We need n points, and I'm just trying to come up with a couple of points that would be easy. We need something bigger than that. We need that if we have n points, we somehow can reuse the calculations in one point to calculate the value in other points, right? But if we have p of 1 and p of 2, p of 1 has kind of nothing to do with p of 2, right? So because it's p of 0 plus p of 1 times 2 plus p2 times 4 plus so on. But what kind of points kind of share similar evaluations? So let's look at the polynomial. P of x is p0 plus p1x plus p2x squared plus so on. So what other point can I take such that this would look very similar to this? What do you think? Oh, there's actually a correct answer already in the chat. We can take minus x. Let's take minus x. What's going to happen? If I take minus x, we'll have p0 plus p1 times minus x plus p2 times minus x squared plus p3 times minus x cubed, and so on. If we remove this minus from inside the power, we can see that every other summand will be negative and all the remaining will be positive. So it's p0 minus p1x plus, again, p2x squared, because minus times minus is plus, minus p3x cubed, and so on. So these two things are very similar to each other. Just some things are negated, right? Okay, so we would like to somehow separate these things into two parts so that we can write similar formulas for p of x of p of minus x, right? Because if you look at even powers, then they are the same, right? And if you look at odd powers, they have different signs. So let's just separate them. Let's say that we have a polynomial a of x, which is just all the even powers, right? p0 plus p2x squared plus p4x to the 4 and so on. And we have a polynomial b of x, which is p1x plus p3x cubed plus p5x to the 5 and so on. So what would be p of x in this case? What do you think? What is p of x if we separated the even degrees from the odd degrees of p? Well, actually, p has both of them, right? So it has both p0 and p1 and p2 and p3, so we should just sum them up. It's just a of x plus b of x. And what about p of minus x? Right? In p of minus x, we still have all the even degrees. We add them, but with the odd degrees, we subtract them. So we should take a of x minus b of x. But other than that, very similar formula, right? If we can calculate a of x and p of x, from these two values, we can calculate both p of x and p of minus x. This already seems kind of like some kind of a divide and conquer algorithm, right? Because imagine that we take, for example, numbers 1, 2, 3, and so on, and half, and also we take -1, -2, and so on, minus and half. Then if we separate our polynomials into even and odd degrees, now we had one polynomial of size n and n points, and now we just have two polynomials, each of size n½ and we need to calculate it in n½ points, right? Because we only need to calculate them in positive points now. This looks very similar to divide and conquer. there are just two slight complications. The first complication is, even though the number of coefficients in these polynomials is n², they still have large power, right? Because, for example, if we go further, this a polynomial at the end has like Pn minus 1 times x to the n minus 1. Let's say that n minus 1 is even. And this one has Pn minus 2 times x to the power of n minus 2. So even though the number of coefficients in these polynomials decreased, halved, the power didn't really decrease. So we would like to fix that. How do you think we can fix that? If you look closely at a, there's actually a way to make a to decrease the power of a by a factor of 2. Let's look at all these powers of x that we have here. We have x squared, x to the 4, x to the 6, and so on. They are not only a power of x, they are also powers of something else. What x squared, x to the 4, x to the 6 are powers of? What do you think? Right. They are also powers of x squared, right? So let me copy it here. So we can actually take another polynomial that I will call p even of x, or let's say px of z, so that it's a different variable. Px of z will have the same coefficients as a, but just x, the powers of x will grow not by 2 every time, but only by 1. So what is going to be? P0 plus p2 times x, p2 times z, right? Just z, not squared, plus p4 times z squared, plus p6 times z cubed, and so on, right? And I want to say that there is a very simple way to represent a of x in terms of p even. What do I need to put instead of z to get this value here, right? So I want p2 to be multiplied by x squared, p4 to multiplied by x to the 4, p6 to be multiplied by x to the 6. So yes, indeed, a of x is just p even of x squared. So I changed the points, but now at least I have a smaller degree. That's actually great. We can do the same trick with b. It will be slightly different because these degrees are not even, so I can't just divide them by 2. But I want to say that I can almost do the same trick. So if you see, there is no coefficient p0 here, so all the things that I sum up here are divisible by x. So I can take this x out of the equation. So I can say that it's just x times p1 plus p3 x squared plus p5 x to the 4 and so on. And then I can do the same trick with this thing, right? Let's write a polynomial. So here was a p even polynomial. Now we'll have a p odd polynomial, which also just has the same coefficients, but just I multiply them not by increasing by 2 powers of z, but continuous powers of z. So we have p1 plus p3 times x, times z, sorry. We have a different variable, plus p5 times z squared, and so on. And now tell me, how can I calculate b of x using this polynomial? So I need this power to be not 0 but 1, this power to be not 1 but 3, this to be not 2 but 5, and so on. So I do the same trick as here, right? I put p odd of x squared, but now I will get p1 plus p3x squared plus p5x to the 4 and so on. So now I need to multiply everything by x also, right? So these are our formulas. A is just p even of x squared. B is x times p odd of x squared. And if we come back to where we actually wanted to use these, right? We wanted to use those to calculate the value of p. So p of x was a plus b, p of minus x was a minus b. So now let's write that in terms of our polynomials p even and p odd. So p of x is just a plus b, right? A is p even of x squared. B is x times p odd of x squared. Okay. Now let's do p of minus x, right? P of minus x was a minus b. We again put the same things, we just subtract them. So it's p even of x squared minus x times p odd of x squared. And this is our holy grail. This is the most important formulas that we have here, right? So if we have these numbers, I don't know, 1, 2, 3, and so n half, and minus 1, minus 2, and so on, minus n half, and we had a polynomial of degree n minus 1, now we have two polynomials, p even and p odd. Each has a degree just n half, and we need to calculate them in numbers 1 squared, 2 squared, and so on, and half squared. Only n half points we need to calculate them in. And here also 2 squared and so on, and half squared. Fascinating, right? There is just one small problem. We would like this to be some kind of divide and conquer. But we cannot do more than one step, right? We liked the idea that we have the points where we evaluate, they are broken down into pairs that are negatives of each other. But after one iteration, all our points are squares, and all squares are positive. So we can't break them into pairs again. So this would be a great divide and conquer, but for some reason it doesn't work. We need to somehow avoid this problem. And that will be what we're going to do for the rest of the lecture. I just need a quick break to slightly change my setup. I hope you also are okay with taking a break. I'm going to be back in like 1 minute or 2 minutes. Okay, but I need to change my setup first. Okay, I'm back. Sorry about that. I had to plug in my charger. So let's continue on our journey, right? Just in case, write in the chat that everything works and you can hear me well the same way as before. So we want some kind of divide and conquer algorithm, right? And for example, if n would be equal to 1, that would be the base case, we would just want to have a single point where we evaluate our polynomial, right? Let's say that this point is just 1. When n is equal to 2, we want to have some points such that at the next level, right, we have n is equal to 1, right? N halves on the next level of our recursion. And then our point would be 1. But on the next level, we square our values, right? So we want two values such that if we square them, we get 1. So we want some kind of roots of 1. What are the roots of 1? Roots of 1 are -1 and 1. But now if we have more than 2 coefficients, we need more than 2 points. So for example, the next level would be n is equal to 4. And there we need some points such that after squaring them, we get -1 and 1. For 1 it's very easy, right? We just have -1 again and 1 again. But for -1, we want to find some kind of values x such that if you square it, you get -1. That's absurd. That doesn't exist, right? Any number, if you square it, you get positive, or at least non-negative, right? So that should be impossible. Well, we'll see whether it's impossible or not. Actually, it's not that impossible. We're gonna figure out how to do that. Maybe you've heard of how to do that. To do that, you need something that's called complex numbers. Also, you've heard maybe of a term imaginary numbers. And to be honest, they are not that complex, neither they're that imaginary. And it's actually kind of a philosophical question of what numbers would you consider to be real? Not in terms of real numbers, but just what numbers do actually exist and which don't. And actually real numbers are called like that kind of because they're supposed to be real, existing in the real world, but that's also kind of questionable. Like the most natural numbers, as it stands from the name again, are natural numbers, right? They exist in the nature. I don't know. I have 5 apples. It's something that is there, right? Then you can go to integers. And I want to say that integers are already not real. They don't exist. Like even when 0 was introduced as a number at some point, like people were not sure about that, because why would you need a number for absence of anything? Numbers are supposed to represent how many there are. What does it mean to be none? But if 0 is a reasonable number, I want to say that negative numbers are definitely not reasonable. So for example, imagine that I had 4 apples and you took 3 apples away from me. This makes sense. Now I have 1 apple. But what if I had 3 apples and you took 4 apples away from me? What is that even supposed to mean? That doesn't make any sense, right? We write that I have minus one apple. Apple. Oh my god. But that doesn't make any sense, right? And actually, until like 18th century, negative numbers were not a real thing, because what does it mean? It doesn't exist. It can't mean anything, right? But because we live in a world where these numbers are taught in, like, I don't know, 2nd grade or whatever, 3rd grade, maybe, I have no idea. We just assume them to be reasonable, even though they're not. I don't know. And the same way as, what do you mean subtract 4 from 3? This doesn't make any sense. The same way we can think about this equation. Yeah, it doesn't make sense, but it does make sense to just introduce such a notation. We just call this -1 apple. And if we do that, we can solve some interesting problems with that, even though it kind of doesn't make sense on the intermediate step. And the same thing will be with complex numbers. So we just introduce such a concept, even though it feels weird, but then it's going to help us solve complicated problems. So for example, if we have x squared is equal to 16, it's very simple to solve such an equation. We know that x is equal to 4 or x is equal to -4. But if you want to solve x squared is equal to -16, we don't know how to solve them, right? We say that, no, this doesn't make any sense. We only have real numbers, right? So we said that we have natural numbers, then we have integers. You can go one step further to get rational numbers, and then you can get real numbers. Real numbers are the whole number line. How can there be more than the whole number line? Everything on this line already exists. But actually, we're going to go even one step further, and we're going to introduce complex numbers. So, as I said, you cannot subtract 4 from 3, so we just introduce the notation that does that. Let's do exactly the same thing. We don't know how to solve this equation because it's not solvable in the numbers that we know. But let's introduce some new number. Let's introduce the new notation. That's going to be the answer to this equation. Well, probably introducing a number such that its squared is -16 is very arbitrary. So let's try to find the simplest such example. The simplest such example is x squared is equal to -1, right? And I'm gonna just define I to be a number such that I squared is equal to -1. It's the definition, it's not the property or whatever. I just define it to be this way, right? And then, for example, if I already imagine, again, imagine, right? If I already imagine that such a number exists, I want to say that it should be simple now to solve this equation. Which number squared is -16 if I know that I squared is -1? What do you think? Okay, maybe it's not that simple, but I want to say that the answer is 4i, for example. Why is it the case? Let's square it, right? It's going to be 4 times I times I. So it's 16 times I squared. I squared by definition is -1. So it's 16 times -1, or -16. And there is obviously another solution. You can always add a minus, right? And then this minus would disappear. For now, this looks weird, right? We just kind of imagine that something exists, and then there are some funny formulas. But I want to say that this actually makes sense. Let's understand why it makes sense. So technically, you can already just introduce this and now do algebra with it, right? So for example, if I have two numbers, I don't know, 2 plus 3 times I can add 5 minus 7i to this. There's no problem. It's the same way as if I would be some variable x, right? I have 2 plus 5, 7, and 3i minus 7i, so minus 4i. I can also multiply 2 plus 3i times, or let's say, I have a better example here, 3 plus 2i times 2 plus I. I just multiply every pair of these things, right? 3 times 2 plus 3i plus 2i times 2, so 4i plus 2i squared. But I know that I squared is -1. So this is just minus 2. So I have 6 minus 2, 4, and then 3i plus 4i, 7i. So this is just the answer. You can do algebra like that. But that doesn't make any sense, right? There's no intuition behind it. What is that even supposed to mean? What these numbers are? Like, maybe this even leads to some contradictions. I don't know. But let's try to get some intuition about that. So what even is a number? So for example, when I add a number, what does that mean? I want to think about it as some kind of function, right? I can take any number and add 3 to it. So add 3 is some kind of function, right? I take any number x and I add 3 to it. And I want to say that it's some kind of action that I can do on the number line. So for example, we had 0, 1, 2, and so on, minus 1, minus 2. So if I apply this action plus 3 to the number line, what happens to it, right? 0 becomes 3, 1 becomes 4, 2 becomes 5, minus 1 becomes 2, and so on. So this action is just shifting everything by 3. I just shift the whole number line by 3 units. And this is what plus 3 means. Minus 3 just means shifting the other way around, shifting to the left rather than to the right. Now I have a different question. What does multiplying by 3 means? Right? What action do we apply to the number line to multiply by 3? Right? 0 stays in the same point. 1 becomes 3. 2 becomes 6. Minus 1 becomes minus 3, and so on. So we actually stretch our number line. So here we shift, and here we stretch. So we kind of add a pin to 0. I don't know how to draw pins. Pin 0, and then we think that it's some kind of elastic thing, and we stretch it by the factor of 3. Right? And if you think about multiplication in this way, then even negative numbers don't make any sense, right? What does it mean to multiply by minus 1? What does it mean to stretch by minus 1? Stretching by 1/3 makes sense, right? It's just shrinking. But what does multiplying by minus 1 mean? Actually, it's just flipping the whole number line, right? So we had a 1, 1 becomes minus 1, minus 1 becomes 1, 2 becomes minus 2, and so on. So we're just flipping the whole number line symmetric to 0, right? This is some kind of symmetry. And if you have multiplying by minus 3, finally, then what is that? That's just a combination of 2. You scale by a factor of 3, and then you flip. Or you do the other way around. You first flip, and then scale by the factor of 3. Right? And if we have some kind of equations, like we want to find x such that x squared is equal to 9, you can think about it this way. You can think about it, we take the number 1, and then we apply 2 actions to it. We first multiply it by x, and then we multiply it by x again, and we want it to become 9. So we want some kind of stretch, such that if we apply it twice, the number 1 jumps to the number 9. What kind of stretches, if applied twice, put number 1 into 9? Well, we can just multiplication by 3. You stretch by 3, and then you stretch by 3 again. This way you stretched by 9. You can also multiply by minus 3, right? Because if you flip, stretch, then these 2 flips just negate each other, right? This is because minus 1 times minus 1 is just 1. They negate each other. If you flip twice, nothing changes. And I want you to think about complex numbers exactly the same way. So adding is just shifting. And multiplying is just some kind of action that we apply on our numbers. Yes, exactly. This is exactly the same as negative times negative is positive. Because multiplying by a negative is flipping. Flipping twice is not doing anything. So now we have our number y. This is 0, this is 1. And we want to solve the equation x squared is equal to minus 1. So another way, again, we take the number 1, we apply some action twice, and we get minus 1. What kind of action, this is minus 1, sorry. What kind of action with a fixed 0 we can apply to 1 such that it becomes minus 1? On the number line, this doesn't make any sense to us, right? Because if we just do 2 stretches, 1 will be still on the positive side. If we do a negative thing, then we flip twice, and 1 will still be on the positive side. But just try to imagine what kind of action would move 1 to minus 1 if we apply it twice. So let's think about this flip that we have, right? When we multiply by minus 1, what is this flip? I want to say that this flip, you can think about it just as a rotation by 180 degrees. I take my number y and I rotate it 180 degrees. So what would be half of that action? So I want some action that if I apply it twice, it's a rotation by 180 degrees. Well, that's just a rotation by 90 degrees, right? Let's imagine that actually there's not only number y, but the whole number plane. There's another dimension. And I can rotate by 90 degrees. And then I can rotate again by 90 degrees. If I do it twice, now I get to minus 1. So this action that should be applied twice to 1 to get to minus 1 is rotate by 90 degrees. And this is exactly what our number I is. Number I is the number 1 rotated by 90 degrees. So if you have this coordinate system, then 1 is just the unit on the x-axis, and I is a unit on the y-axis. Note that now you can represent any kind of number on this plane. It has some x-coordinate, a, it has some y-coordinate, b, and you can write this number as a plus bi. Oops. Right? Because we know that what does multiplying by b means? It means that we stretch by b. We had I, and then we stretched it by b, and we get this point here. And then we add 2 numbers together. We know that adding a number is just a shift. So we had 0. We first shifted it by a, and then we shifted it by bi. Sounds awesome? I hope it does. And this x-axis is called the real line, and this y-axis is called the imaginary line. Because these numbers were supposed to be real, and this was supposed to be imaginary. Like, this was actually kind of a joke name. If I know correctly, like, the first person who introduced this name imaginary was kind of trying to mock these numbers because obviously they're not real. They don't make any sense. But at the end, this name just kind of stuck, and now we use it. So we have real numbers. These are the numbers that we know. There are imaginary numbers, which are basically any kind of real number but times I. And then we have the whole plane. These are called complex numbers. And complex numbers can be just represented as a sum of a real number and an imaginary number. So we understood that we have kind of some actions, right? All multiplication is action. So if we multiply by a real number, it's a stretch. There is some stretches and there are some rotations, right? Multiplying by minus 1 is a rotation by 180 degrees. multiplying by I is a rotation by 90 degrees. But what does it mean in general to multiply by some number? I want to claim that this action works exactly the same as before, right? So what was an action of multiplying by 3? We pinned the number 0, and then we stretched such that the number 1 moves to number 3. Multiplying by -1, we fixed the number 0, and then we stretched somehow, or in this case, rotated by 180 degrees, so that 1 moves to -1. Multiplying by I is a rotation by 90 degrees because we fix 0 and we move 1 to I, so we rotate by 90 degrees. And this works in general. Any kind of multiplication by any real number z is just we pin down 0, we take 1, and we kind of do this stretch and rotate such that 1 becomes z, right? So we can think about it first as we kind of rotate, and then we stretch by the magnitude of z, and we do that with the whole plane. This is kind of hard to explain on this whiteboard, so let me show you some visualization that I found on the internet. It's in one of the, it should be somewhere in the description anyway. So here we have this number z, which is equal to 2 plus 3i. Why is it equal to 2, 3? Because its x coordinate is 2 and its y coordinate is 3. And I have the number 1. And I have here this interesting thing where I can move this number. And if I move this number, this whole grid of numbers also moves with me, you see? And I want to say that wherever I move this number 1, this would multiply my whole grid, so all the numbers on the plane, by this number. So for example, I can multiply by 0, boom, everything collapsed. Because if I multiply anything by 0, I get 0. And if I multiply by I rotated everything by 90 degrees. Do you see? Whoop, whoop, I did a rotation. If I multiply by 3, I just scaled everything. You see, I'm just scaling. If I multiply by -1, I just do a symmetry, or a rotation by 180. But now, let's try to multiply by this number z, 2 plus 3i. What's going to happen? I take this point and I move it here. This is a combination of a rotation and a stretch. And to think about it simpler, we can just first rotate and then stretch, right? They can be kind of separated from each other. So multiplying by any kind of complex number is a combination of a stretch and rotation. Great. Now we can go back to what we actually are trying to do, right? Complex numbers for us are not the goal. It's just some kind of tool that we use. So imagine that we had this picture where we had our problem of calculating the polynomial in endpoints. And then we reduced it to a smaller problem when we squared all the values. If they were negative positive pairs, then now we have n half points rather than n points. And then we had this picture where we would like to have, on the last level of recursion, we would like to have 1. On the previous level, we have two numbers such that their squared are 1, so it's -1 and 1. And on the next level, we want 4 numbers such that if we square them, we get -1 and 1. And now we know how to do that, right? We have 1 on this level, -1 and 1 on this level. Here, square roots of 1 are -1 and 1, and square roots of -1 are what? Square roots of -1, we know that there is I, but there's also -I, right? Because always if you have a negative, if you square it, it doesn't matter. But why does it work, right? Because what is -1? It's rotating by -90 degrees. But if you rotate by -90 degrees twice, it's the same thing as rotating by 90 degrees twice in the positive direction. So it doesn't matter. Anyway, both of these things applied twice give you -1. Okay, but we want to go further, right? We want to do this again and again and again. We want to have divide and conquer, so we want to have recursion. So here it's easy again, right? We already did this. We want to just take square roots of these numbers. So square roots of 1 are -1 and 1. Square roots of -1 are I and -I. But what would be the square roots of I and -I? So you want some action that if you apply it twice, you get to I. So it's some action. If you apply it twice, then 1 moves to I. So it's half of the rotation by 90 degrees. What is half of the rotation by 90 degrees? It's just a rotation by 45 degrees, right? So if you rotate by 45, then we rotate by 45 again, we get to I. So the square root of I should be some kind of number that is like a rotation by 45 degrees. And then we can do this in general, right? So for example, if we have like k levels of recursion, at the end we have 2 to the k numbers, and we want that if we power them k times, if we square them k times, then they get to 1. So we have like n numbers at the end, right? And we basically are interested in the solutions to the following equation. X to the n is equal to 1, right? On this level, we have just x to the 1 is equal to 1. X squared on this level is equal to 1. X to the 4 is equal to 1. These are all the numbers, such that if you power them to the 4th power, you get 1. X to the 8 is equal to 1, and so on. Right? We know that in real numbers, sadly, this only has like 1 or 2 solutions. But in general, this is some kind of a polynomial, right? X n to the -1 is equal to 0. In general, it could have at most n solutions. And here's like a secret. In complex numbers, all polynomials of degree n have exactly n roots. This is not that important for us because we don't care about roots that much, but it's just a nice fact. It's called the fundamental theorem of algebra. Right, but what we want is to find numbers such that if we take them to the nth power, we get 1. Again, we know that numbers are just actions, right? So we want to take 1 and apply some action n times and get 1 again. We'll get back to the recursion a little bit later. We just need to finish with complex numbers here. So let me remind you, right? Multiplying by -1 is a rotation by 180 degrees. If we apply it twice, we get back to 1. Multiplying by I is a rotation by 90 degrees. So if you apply it 4 times, you get back to 1. What would be the action that if you apply it m times, you get back to 1? What do you think? I think we have a larger delay right now. Yes. So we just need to do a rotation by 360 degrees over n. If you rotate by this amount n times, you will rotate by exactly 360 degrees. Degrees are not that great for us. Let's write them in normal way. So it's 2 pi over n, right? Rotation by 2 pi over n. And we also don't need any stretch. We only need rotation. So what kind of number would not give us any stretch, right? we know that if we move 1 to any number, it's a rotation plus stretch. So that there's no stretch, we need that after we rotate, we're already there. So actually this number should have distance from 0 should be 1. So all these numbers should live on a circle of radius 1. And the angle, as we said, should be 2 pi over m. This would be the right rotation. But actually, not only 2 pi over n works. Also, we can take this 2 pi over n, this angle alpha, and we can take alpha. We can take also 2 alpha. Because if we apply alpha n times, we get full rotation, 360 degrees. But if we would take 2 alpha and apply it n times, then we would get 2 full rotations, right? 720 degrees. But 2 full rotations is still doing nothing. It's still moving 1 to 1. So actually we can take any multiple of alpha. Because if we take any multiple of alpha, then this action would be some number of full rotations. So actually these roots are just all numbers that look like this. 2 pi times j over m, where we can take j to be equal to 1, 2, 3, and so on. And at some point we're gonna cycle, right? So if j is equal to m, this is just 2 pi, so this number will be just 1. So let's say that it's just 0, 1, 2, 3, and so on, n minus 1. And this is exactly the n roots of this equation, right? These are all the actions that if we apply them n times, we get back to 1. And this is just taking our circle and putting on equal distance n points around the square. So for example, if we have numbers that are squared are equal to 1, they are just 1 and minus 1. We put 2 points on the square. If we care about applied 4 times, then we also add I and minus I. Now, if we care about 8 points, right? We should put points here in the middle. All these points will give you what we want. If you want 16 points, you again put points here in the middle and so on. I think you get the gist. Okay. But it's cool, right? We know that every number can be represented like as some stretch, right? Some real number by how much we stretch and an angle, right? We don't care about the stretch. We always want the stretch to be 1. But this is not how we represent complex numbers. We represent complex numbers as a sum, like real number plus I times a real number, right? So we are interested in this number that is on the unit circle alpha degrees away from 1. How can we write the coordinates of this number? Sorry, I have a problem. How can we write the coordinates of this point? Well, here some simple trigonometry will come to play, right? There are just probably, functions. They are called cosine of alpha and sine of alpha. And their definition is if you have an angle alpha and we have a right triangle and it has sides x, y, and z, then by definition, sine of alpha is x over z. So this side by the hypotenuse. And cosine of alpha is the other way around. We take this value and we multiply it by this. Note that in our case, we have this right triangle, but this is equal to 1, right? Because this is a unit circle. So the length of the hypotenuse is 1. So z is equal to 1. So actually, sine of alpha would be, okay, this is probably a better way to write this. Let's change them. This would be x, and this will be y, right? Because this is the x coordinate. So in this case, y is just equal to sine of alpha, and x is equal to cosine of alpha. So actually, if we know the angle, we can easily get this complex number. That's not that hard. So actually, this number that has angle stretch 1 and angle alpha is just cos alpha plus I times sin alpha. And if you want to add some stretch, then you multiply it by the stretch, but we don't care about that. Our stretches are 1. Okay, that was intense, but now we know basically everything we need to know about complex numbers. I hope this makes sense, right? We understood that multiplying by a complex number is pinning the 0 and then moving the number 1 to that number. This is a rotation and a stretch. As I said, we don't really care about numbers that are not on the unit circle, so we only care about rotations. And now if we start from n, we want to evaluate our polynomial in n points. We want them every time when we square them, they form a positive negative pair. And what is a negative pair, right? We know that multiplying by -1, like negative is multiplying by -1. And multiplying by -1 is just a rotation by 180 degrees. And note that here, all these numbers are always paired by 180 degrees, right? So initially we had these 16 points. When we square them, then they become these 8 points. When we square them, then they become these 4 points. When we square them, they become just -1 and 1, and then when we square them, we get 1. So we want to start with the solutions to this equation, x to the n is equal to 1, and then square them, square them, square them, square them, and this will be our algorithm. So the initial points where we're going to try to evaluate our polynomial are points of the following form. It's cos of 2pj over n plus I times sine of 2pj over n, right? And that's basically the end of our algorithm. Let's just try to remember how our algorithm looked like, right? So we started with a polynomial p. We wanted to evaluate it in n points. J is just an index. We take j from 0 to n-1. We take all such points. We want to evaluate it in n points. We create these polynomials p even and p odd, such that to calculate n values of p, we just need to calculate these two smaller polynomials in squares, right? And because our values that we are trying to evaluate are positive negative pairs, if we square them, now there are twice as little numbers. So we're reducing the problem of multiplying, evaluating n points of a degree n polynomial to two problems where we're evaluating degree n half polynomial in n half points. So this is a divide and conquer scheme. And we do this in a divide and conquer manner. Then we move to n4th and n4th and so on. So let me bring this formula back to where we are. We start with these points for all values j from 0 to n-1. And we use this formula to move to a polynomial of size twice as small. So here we have size m, then we have two polynomials of size n half, then we have four polynomials of size n to the 4. And this is basically the same thing as we do in merge sort, right? We just split into two halves and then combine it somehow. And because on one level of recursion we do only some linear amount of work, right? We first just take the polynomial p and break it down into p even and p odd, right? We just write separately the even coefficients and odd coefficients. Then we recurse. And then on the way back, we just need to combine these values this way. It just takes linear time, right? For every xi, we just take some value from even, some value from odd, maybe multiply by x, sum them up. It takes constant time. So on one level of recursion, we work in linear time. And how many levels of recursion there are? Well, every time we have, so there's log n levels of recursion. On every level of recursion, the whole work is n, right? And there are log n levels of recursion. So the total time complexity of this algorithm is n log n. Halving will work exactly the same way, right? Because we made sure that when we square, every time we square, we still have negative positive pairs. Let me give you an example, right? So let's say that we start with these 8 points. 1, I, -1, -I, and these points that have some weird coordinates. Like they are 45 degrees apart. Initially, we want to calculate in all these 8 points. When we go to the next level of recursion, we are asked to calculate in all squares of these numbers. What will be the squares of these numbers, right? We have 0 degree, 45 degree, 90 degree, 135 degree, 180 degree, and so on, right? 8 points. If we square them, their angles are multiplied by 2. So this becomes a 90 degree. So this number squared becomes I squared becomes -1. So it's 180 degrees. 135 degrees becomes, oh my God, too complicated, 270, which is I'm super confused. This? No? Yes, this. 180 becomes 360, and so on. So actually, all these numbers, when squared, becomes these 4 numbers. And they again form positive negative pairs. When we square these 4 numbers, right? 1 squared is 1, I squared is -1, -1 squared is 1, and -I squared is 1. We get these 4 numbers, and they again form positive negative square pairs. Now we square them again, and finally we get only the number 1. So at every iteration we do the same thing. We did such a thing that on every iteration when we square, the numbers are still positive negative pairs. So initially when we had real numbers, the problem was that after one iteration, all the numbers are positive, so there's no positive negative pairs. But if we take evenly spread points around the circle, then when we square, so initially we had 2 to the power of k points around the circle. When we square them, we get 2 to the power of k minus 1 evenly spread points. Then we get 2 to the k minus 2 evenly spread points, and so on. And this is our whole algorithm. Now let's try to implement it. Note that our algorithm works only for a power of 2, so we will increase the size of our polynomial to the nearest power of 2, which will not change the time complexity. It's just important to remember. So actually, if we're using C++, there are already complex numbers embedded into the language. So we can include complex, or if you use bit C++.h, they're already there. And now you can use complex numbers. they are actually a template complex, and then you put some type, integer or like a real type that you use for your coordinates, right? So every number is like I plus bi, and what these numbers a and b will be. Will they be integers, long, double, whatever, right? Because we care about these numbers in a circle, these numbers are not going to be integers. So we need doubles there. So we're going to use complex double, the same way as with vector of something, right? To not write this thing every time, let's make a shorter name. Let's call it CMPL, standing for complex. And now we can use it, right? So for example, we can create a complex number by just writing 2 of its coordinates. This will be just 3 minus 4i, right? I can create another number, t, which is 2 plus 5i. I can also create a complex number from a real number. It will be just 2 plus 0i. And then I can do some operations with them. This will output 28 plus 7i. I just write multiplication, it will be complex multiplication. Probably we will not be interested in outputting complex numbers, but we're interested in using them. And also there are 2 interesting methods that we'll care about. Actually one, which is z.real. This method returns us the real part of this complex number. So this number is 3 minus 4i, this will return 3. And here there is another called imag. So it returns the imaginary part, which in our case is minus 4. This is everything we need to know about complex numbers in C++. And now we are ready to write our algorithm. Great. So because we care about all these angles, let's write our recursive algorithm. So we will have this FFT algorithm, right? And yeah, I guess I didn't tell you, but this transformation that I told you, so we had P0, P1, and so on, Pn-1, the coefficients, and we convert them into the values of the polynomial P for these numbers of this form, right? Numbers on this circle. So cosine of 2pj over n plus I times sine of 2pj over n. For all these different j from 0 to n-1. This transformation is called the fast Fourier transform. And the other way around is called the inverse fast Fourier transform. Specifically for these points on the unit circle. So we get our coefficients as input, right? And we return the values in the endpoints. So n is the size of p, so it's 1 larger than the degree of p. And now we first need to break our polynomial into 2 halves. Let's go back, right? Remember that we had a polynomial p. We understood that if we take p of x and p of minus x, then they differ only that odd summands are negated. So we created 2 polynomials that one contains all the even coefficients and the other contains all the odd coefficients. And using these 2 polynomials, p even and p odd, we are able to reconstruct our values of p. Right? So let's create these 2 polynomials. It's simple. We just separate the values in p into even and odd ones. So we have p even of size n½ and p odd of size n². Remember that we always assume n to be a power of 2. And now we just go through all the indices, and from 0 to n², and p even j is equal to p 2 times j, and p odd of j is equal to p 2j plus 1. So all the even ones we put in p even, All the odd ones we'll put in p odd. Now we recursively run FFT on p even, and we get the values of this even polynomial in all the squared numbers, right? So for all x, we will find p even of x squared, right? And now we do the same for odd. We run FFT of p odd. And now we should just use this formula to reconstruct our initial values. It's involved with sine and cosine, just we didn't finish our algorithm yet. So we want to calculate our values. So we want to calculate values of p, and at the end we will return them. So how are we going to calculate them? We have all these different powers here, right? And let me draw you a picture. So again, we have imagined that n is equal to 8. We have the 0th power, the 1st power, the 2nd power, 3rd, 4th, 5th, 6th, 7th, right? And on the next level of recursion, we have twice less numbers. So there, this is the 1st power, this is the 0th power, this is the 1st power, this is the 2nd power, and this is the 3rd power, right? And when we take this number, we care about, so imagine that this is x, right? To calculate x, to calculate p of x, let me copy this again. We care about the values of p odd and p even in the square of x, right? What is the square of x? Let's remember, right? We apply the rotation twice. This was the rotation by 45 degrees, so twice it's here, so it's I. So for the first value in our answer, we care about the second here, but the first in the recursive call, right? For the second one, it's I, so its square is -1. So we care about this value. This was 3. For 3, twice is this. So we care about the third one. And so on. And you can actually see that these indexes are the same, right? So the first half of the indices, like 0 also cares about 0. These are the same indices because in the next iteration we have twice less indices, right? So okay, sorry, I hope it's clear what I'm trying to say. Okay, let me explain it in a different way. So for example, you have 2pj over n, right? This is the angle. If you square this value, you will double the angle. So it's 2p times 2j over n, right? And on the next level of recursion, we have twice less of these angles. So we don't multiply by n, but we multiply by n half. So it's 2p times something over n half. But actually this value is equal to 2p times j over n half, right? You can move this 2 to the top. So actually the square of the jth value from our level of recursion is just the jth value on the next level of recursion. The only problem is just that they round up around the, so because we have twice as less, they actually pair together, right? So the 0th, 1st, 2nd, and so on, n half minus 1 correspond to 0th, 1st, 2nd, and so on, n half minus 1 in the next one. But also these two numbers are positive negative pairs, so they all doubled get to I. So actually n halved plus 1, and so on, n minus 1st also correspond to these ones. So when we want to calculate the jth value here, we use it to, when we had the jth value in the next web of recursion, we use it to calculate the jth value and the j plus n halved value. And this will be the formula that we use, right? So x will be like xj, minus x is just x n half plus j in our order. And these x squared are just x prime j, where prime is just the next level of recursion, right? Okay. Sorry, I think that was a little bit confusing, but I hope that was understandable. And we know this, right? These are just the values in val even. We know this. This is just the value in val odd. And now we just need to combine this using this formula to get the values of p of x and p of minus x. So we iterate j from 0 to n half. And we want to create, what do we have, right? We want to calculate p of x. We already have this. We already have this. The only thing we need is just x, right? So we want to get the number such that its angle is 2pj over n. We already know how to do that. We had a formula for that somewhere, right? It's just cosine of 2pj over n and sine of 2pj over n, right? Let's just create a complex number vj, which is just the cosine of 2 pi j over n and sine of 2p j pi j, sorry, over n. One problem is that we don't have pi here. We just need to make a constant that is equal to pi. I don't know how you do this normally in geometry problems. I always use this a tan 2 function, and a tan 2 of 0 and minus 1 is pi. Here you just basically kind of give a sine and a cosine of a angle, and it gives you the angle. You can also use like arctangent, right? The tangents of pi is arccosinus, right? Arccosine. So cosine of pi is minus 1, so you can take arccos of 1. Or there's also a constant m pi if you include the C math library, but I normally just do it like this. Okay, so we have this wj, which is our x, right? And now we can calculate the value of p, the jth one, and we can calculate the value of p, the j plus n halved. Right? So what do? We want to count this thing is p val j. This is p val j plus n half. What is this? P even of x squared is just the jth value of p even. So we take val even j, and then we want plus x times the odd thing, plus vj, wj, times val odd of j. And here we have exactly the same formula, we just subtract instead of adding up. And this is the end of our algorithm. We talked about it for so long, but at the end, it's just like 15 lines of code. This is everything. Maybe somebody sees what mistake did I make? I forgot about something. We have some kind of recursion here. What did I forget in this recursion? I want to say that we never terminate this recursion. That's not good. So we need to have some base case. Yeah, no base case. So what is the base case, right? The base case is when n is equal to 1. So we have only one coefficient. So actually p of x is just equal to p0. How to evaluate this polynomial in any point? Actually, we're evaluating in the point to 1, but it doesn't matter. In every point, it's just p0. So actually, its value is equal to its coefficient representation. So if n is equal to 1, I just return p. It looks kind of weird because p is a polynomial and I'm returning the values, but just that the coefficient of this polynomial is equal to the value. Good. We have one slight problem. It looks like we only did the easy part of our algorithm. Because if you remember, our algorithm for polynomial multiplication is we evaluate, multiply, and then interpolate. And we thought of interpolation as something that is much more complicated than evaluation. So you could think, oh no, it's been so long and we're still only like halfway done or something. But actually I want to say that we're almost done. Interpolation will work almost exactly the same way as evaluation. The cool trick that I'm going to show you actually has nothing to do with fast Fourier transform. It can be applied in many different, okay, not many, but a bunch of different contexts in competitive programming. And this trick, I don't think it has any specific name, but I like to call it time reversal. So you take some process and you imagine that you reverse the time. Imagine that you're like some kind of a time lord that can inverse time, reverse time. So normally at this point, people go deep into some math, draw some matrices, find some inverse of a matrix. That's too complicated. Let's not do that. So I want to tell you that evaluation is just the opposite of interpolation, right? So we have two, I already drew it somewhere, right? We have this picture. That there are these two worlds, coefficients and samples. And what we did is evaluation, right? We learned how to move from coefficients to samples. But interpolation is just the opposite operation, right? If I have some polynomial and I evaluate it, I get some values, whatever, and then I interpolate it back, I get the same polynomial. And that's the great property, right? We know already how to do this. Now we want to learn how to do this. So what did we do? We had P, we evaluated it. We had Q, we evaluated it. We multiplied them. And now we have the values of R in these points around the circle. And now we somehow need to get R. Right? We don't know how to do this action, but actually we know how to do this action. This action is just evaluation. Note that we got these values not from evaluating R, but if we would evaluate R, we would get exactly these values. And now I just want you to imagine that you got these values from evaluating R. And everything we need to do for interpolation is somehow to try to inverse this process. Right? To do the opposite action, you just inverse all the actions in the opposite order. So let me give you an example. I have a Rubik's Cube here, and I can do some number of actions on it, right? And I didn't make it too shuffled, but anyway, you can shuffle it significantly. And then there are some complicated algorithms that tell you how to solve the Rubik's Cube from any configuration. But my configuration is easy because I know what actions I applied to get to this state. So I can just take these actions and unapply them in the reverse order. So I just do this, and I come back, right? So for example, I move this up and this to the right. Now I need to do the opposite, right? I undo the right rotation, so I do the left rotation, and I undo the up rotation, so I move it down. So if you have any sequence of actions, like action 1, action 2, and so on, action n, to move back, you just do the opposite of an, then you do the opposite of an-1, and so on, you do the opposite of a1, and then you will move back. So actually, right, if we have our values of r, we know that if you would have r, you could get the values of r using this algorithm. But we want to do the opposite thing. So we just take this algorithm and we just undo this algorithm, right? This idea sometimes exists in other contexts. Like for example, if you have union find with drawbacks, maybe you've heard of that. There, like in union find, you can only unite sets, you cannot split them. But if your splitting operations are just the opposite of your uniting operations, you can do that. You just do some operations and then just undo them. You just remember which cells of your memory changed in what way, and you undo these operations. And then you can go from the later state to the earlier state. Let's just do the same thing here. Like, not all operations that you do in programming are reversible. So for example, if I had some two variables a and b, they had some values, and then I did a equals b. I cannot undo that, right? I don't know what a had before b was here. But if I do a plus equals to b, I can undo this operation. To undo this operation, I just subtract b, and now a comes back to its initial value. And if you look closely, you can see that all operations we have here are actually reversible. And because they're reversible, I can undo this algorithm. And undoing this algorithm would be the inverse of this algorithm. That's exactly what we want, right? We want to find an algorithm that does the inverse operation of what this algorithm does. So let's just write the inverse of this algorithm. So this will be the inverse fast Fourier transform. It gets as the input, so we go from bottom to up, right? We go bottom up, we do the actions in the opposite order, and we do it, reverse the actions. Rather than applying some action, we reverse it. So instead of adding something, we subtract. So we get initially our values, right? Values of p. And we want to get our coefficients, right? So first, we again have n is equal to this. They have the same size. And we have our corner case, right? In the corner case, we did nothing. So to undo nothing, we also do nothing. That's great. If n is equal to 1, we return our val p. Otherwise, we have our value p, and we need to get our value even and value odd. Okay? So we create these vectors, value even of size n½ and value odd of size n². And now we're iterating over our vector in the opposite direction, actually, right? So if we're being very serious, we should go in the other direction of our cycle. It actually doesn't matter because these actions inside the cycle are independent from each other. But to make this more dramatic, let's do the opposite. And now here we calculate the value of p from value even and value odd. But here we have the opposite, right? We have the value of p, and we want to calculate the value of even and value of odd. How to do that, right? Let me copy this formula to the board so that it's easy to think about it. So val pj is equal to val even j plus wj. Okay, it's too complicated. Let's call this a, b, c, d, right? So we have a is equal to b plus wj c. And we have d is equal to b minus wgc. This is how we calculated them. But now we know a and d, but we don't know b and c. How to do that? Yeah, somebody in the chat is saying correctly. Let's add them up. What is a plus d? A plus d is 2b, because b's add up, and these things cancel each other. So b is actually a plus d halved. And how do we get c? Let's just subtract. So a minus d will be, well, b's will subtract, and c's will add up. So we get 2 times wj times c. So c is just a minus d over 2wj. Let's do exactly that, right? So we know that val even of j is just, we need to add these two things up and then half. So it's val pj plus val pj plus n half divided by 2. And for odd, we do the same thing, but we subtract them and divide by 2 times wj. Subtract and divide by 2wj. Let's copy the definition of wj here. Right? We undone all the actions that we did here. Now we have val even and val odd. Now we need to undo the recursion. So we just recursively solve the problem, right? So p even is just the inverse FFT of val even, and p odd is just the inverse FFT of val odd. Now everything we need to do is we need to get p, but that's very simple, because we know that p even stores all the even coefficients of p, and p odd stores all the odd coefficients of p. So we just need to combine them back together into one array. So we just create a new array p of size n. And again, if you see that this array, we can, this cycle, we just do it backwards, right? Instead of doing this, assigning this way, we assign the other way around. And formally, we need to reverse the cycle again, right? But I want to say that it doesn't matter because, again, actions are independent of each other. So we write that p 2 times j is equal to p even j, and p 2j plus 1 is equal to p odd j, right? We do the same assigning, but just the other way around. Instead of assigning from left to right, we assign from right to left. And now we return p. This is our inverse fast Fourier transform. It's just doing all the actions of fast Fourier transform in reverse. As I said, here I'm just, this is not important, right? If your actions in a loop would depend on each other, then it would be important that you undo them in the other order. But here, the actions in a loop are independent from each other, so you can do, you don't need to reverse this cycle, but I just did exactly the opposite of what this algorithm did. I hope this makes sense. And this is magical, right? Because somehow we had this easy problem, kind of evaluation, and we solved it, and then we just have, we didn't do anything smart, right? We did a very mechanical action of just looking at the algorithm and undoing all the actions of this algorithm. And this way we get an algorithm that does the opposite thing. Everything that's left to do is to just write our algorithm that does the multiplication, right? We have basically this scheme that we evaluate one polynomial, evaluate another, then multiply them, and then interpolate. But let's be more specific in our case, right? Because we know that first, the number of points where we evaluate has to be, has to be at most the size of the answer. And also we need it to be a power of 2. So let's write the details. Note that the answer would be probably vector of long, because when you do this polynomial multiplication, you multiply different coefficients and then you sum up these products. So this is probably going to be a very large number, so be careful about that. We have a multiply function that takes 2 polynomials as input. And we want n to be a power of 2, right? So let's multiply n by 2 while it's small enough. We want n to be equal to at least the size of the answer. At the beginning of the lecture, we said that the size of the answer is size of p plus size of q minus 1. So while n is smaller than p size plus q size minus 1, we multiply n by 2. Here you can, this minus 1, you don't need it. You can multiply while it's smaller than p plus q. Just if you evaluate in more points, it's not worse, right? So you can write whatever you want here. Just it needs to be at least p size plus q size minus 1. Now our algorithm, it takes a complex vector as input. So let's convert our integer polynomials into complex polynomials. This is very simple, right? We just create a complex version of this vector of size n, and then we copy the value of p to this vector, right? The size of p could be smaller, so at the end, these values will be just zeros, right? And then we do the same thing with q, complex version of q. We copy everything from q to this complex version of q. Here I'm not doing anything complicated, right? It's just changing the type that we work with. Now we apply fast Fourier transform to both of these polynomials, right? We want to get the values of p in n points. I want to get the values of q in n points. And after that, we know that if we have the value representation, to get the values of the product, you just multiply the values, right? So to get the values of the answer, I just go through all the indices and I just multiply. So value I is p value I times q value I. Now I have the values of R, and everything I need to do is just apply the inverse Fourier transform. So R would be the inverse Fourier transform for the values of I, for the values of R. This is still a complex vector. It's kind of weird, right? Because we want our answer to be the vector of longs, but because our intermediate steps involved complex numbers, we still get some complex number. We just know that the answer is the product of our polynomials, and because our initial polynomials were integers, the answer is also integer, but it's stored in a complex number. So this complex number will always have a form of some like I plus 0 times I, where a plus 0 times I, where a is an integer, right? So we just need to extract this value a from it. And for that, as I talked before, we have this method, zReal, which gives us the real part of a complex number. So we create the answer. So let's call it R complex, right? This is the complex version of R, and this will be the R. And we just go through all the indices. Okay, maybe it's what's better to call this J also, because I is a number. Yeah, it's kind of weird because we use I as a number in complex numbers, and also I is a lot of times index. Rj should be just equal to the real part of the R complex. Here there is a slight problem, right? Because we work with doubles. Doubles don't have absolute precision. So this number at the end, it's not going to be like a plus 0I. It's probably going to be something like a plus minus epsilon plus some kind of epsilon times I. About this epsilon, we don't care. We just ignore it. But here, this will be not exactly the right answer. It will be just approximately. So we should round it to the nearest integer, because we know that the answer is integer. We need to round it. So I will add the round function around it. And note that we work with doubles a lot of the time. So you could think that there are problems with precision. But actually, because we know that at the end, the answer is integer, precision we need is just plus minus 0.5. Let's say plus minus 0.4, right? Because if your number, if your actual thing that you compute differs from the actual value by at most 0.4, you will anyway round it to the nearest integer. It will be the correct answer. So you don't need this crazy precision and in geometry problems like 10 to the minus 9, 10 to the minus 6. If your answer is correct plus minus 0.2 or something like that, 0.4, you're good to go. So now you calculated R, and we just return R. This is the end. This multiply is kind of complicated, like it's a lot of code, but it's useless code, well, like it's meaningless code. It's just like finding the power of 2, then converting an integer vector into a complex vector, then doing the recursion, then just stupidly multiplying, and then going back, then rounding the values. But actually there's no nothing crazy is going on here. So that's all good. So this is the whole algorithm. Right? We have our fast Fourier transform. It's a recursive function that takes a polynomial p. It splits it into two parts, even and odd. It recursively evaluates these two polynomials, and then it takes the values of these two polynomials to find the values of p, right? Here we have twice less points where we evaluate, but because there are squares of our points, and when we square our points, there's twice less points, we can use them to find the values of p using our formulas. Then our inverse fast Fourier transform is just doing all these actions in reverse. Crazy idea, very useful. And then we have a multiply function, which is basically trivial. There's no smart stuff going on here. You just need to be careful. Okay. Again, remember that first, n should be at least the size of the answer. And also the sizes of p and q should be the same, right? You should evaluate p and q in the same points. If you evaluate them in different points, you can't just multiply them, right? You can multiply them point-wise if these points are the same points. So it's very important for this value n to be equal here, here, and in R, and also it should be at least the size of the answer. That's very important. Okay, great. So this is everything, right? We learned how to multiply polynomials in n-log time. We solved the 4,000-year-old problem of how can we multiply numbers faster than n squared. This is great. As I said, there are problems in the description. There is a contest in a group. You can click there. There are a bunch of problems. I would highly suggest you, after this lecture, like today or other day when you're solving the problems, please don't look at my code, don't look at my notes or your notes that you did. Try to remember what we did and try to reconstruct all the steps and try to write your own fast Fourier transform. And then if you find a bug, think about where the bug could be, like exactly what am I doing wrong? Write all the math. And I hope that what we did here today was intuitive enough so that you have in your mind some understanding of what we did. And if you have the understanding, you should be able to recreate it. And recreating an algorithm is one of the most important part of learning it. Just blindly applying it is so much worse. So there's a lot more you can learn about fast Fourier transform. For example, our algorithm is not very fast. Like, it's recursive. It uses a bunch of vectors. It evaluates trigonometric functions all the time. That's a lot of time. Yeah, that is very slow. So there are many ways to make this algorithm faster. And this is one of the things that we're going to do in our next stream, where we're going to have the intermediate version of FFT. But that's not important for us. In the context that I set for you, this version of FFT should be enough. I think with exactly this code, you can solve all the problems. If there is some problem that, I would definitely suggest you for most of the problems, please use your own FFT. Write it down from scratch and use it. But if there is some problem where this is not fast enough, you can copy your FFT from some source, I don't know, from other people. But please only copy the FFT, right? FFT is a very black boxable algorithm. You don't need to know what's going on inside it. You can just use this multiply function. You can just copy it and then solve the actual problem with FFT. But please do it only if your algorithm gets time limit. And actually, if your algorithm gets time limit, it's okay. Just think of it as accepted, right? You will later learn how to do this faster. It's not that important right now. Great. And as I said, in the next stream, we will learn how to do this faster, but this will be my homework for you. Please think about the ways to make this code already faster. Like, I can think of a bunch of ways. For example, we're passing a vector here and we never change it. So we can pass it as a constant reference. This will make it a little bit faster. Then we can also reuse some space. Then we maybe don't need to create all these vectors, and so on. So there are many ways to do this faster. This is the end of the algorithm. I hope it was clear. Today we learned how to multiply polynomials, how to multiply numbers. We learned what complex numbers are, how to work with them. Now we're going to solve a couple of problems using FFT, example problems. It's going to take not that long, I don't know, maybe 10 minutes, 15 minutes. But before I do that, I just want to quickly ask if anybody has any questions. So this is the end of the algorithm. I'm not going to talk about fast Fourier transform anymore. From now on, we just assume that we have this algorithm that does convolution or polynomial multiplication, and we're going to just be using it. Okay. I hope there are no questions. Then let's solve a couple of problems. So the first problem is the problem that we already had, right? Remember, at the beginning, I told you about a problem where we have gold and when you have two knapsacks and you're trying to combine these two knapsacks, right? So we have some items, and you know that for these items, from weight 0 to s, you can, for each weight, you know whether you can achieve it or not. And you have another knapsack where for each value from 0 to s, you know whether you can achieve that. And now you want to combine these two knapsacks. So you want for every value to know whether you can get it as a sum of two values here and here. And then this is an array A, this is an array B, and we do the convolution of A and B. So we create an array C such that Ci is just sum over all j and k such that j plus k is equal to I of AI times Bj. This convolution, this is just an abstract combinatorial thing that has nothing to do with polynomials, but it's done via polynomial multiplication. And now, if both ai and bj are 1s, their product will be 1. So this will mean that yes, it's possible. And otherwise, if one of them is 0, then it's not possible. And then you sum them up, you get even the number of ways to do that. The second problem we're going to solve is, imagine that you have n numbers. These numbers are from 0 to m. And let's say that they're distinct. And you want to calculate the number of arithmetic progressions of length 3. So you want to find the number of triplets in the set of the form x, x plus y, x plus 2y. These problems are not trivial, so I guess it's hard for me to give you time to think about it. You can press pause, right? But I'm gonna just jump right into it. So instead of thinking about it this way, x, x plus y, x plus 2y, let's think about it the other way. We have some middle number, and we have a number that's like some amount smaller and some amount larger. So we have some number a minus b, and a plus b, right? And what is interesting about these two numbers is that a is their average, right? So a is in the middle. In other words, if we sum these two numbers together, we get 2a. So actually, we can learn the number of arithmetic progressions where a is the middle number by just learning the number of pairs of numbers, that sum up to 2a. If two numbers sum up to 2a, then they're of equal distance from a in two directions. So we just take our set of numbers, right? We just write for every value from 0 to m whether it is in the set or not, 0 or 1, and we square this as a polynomial, right? This will tell us for every value from 0 to 2m how many ways there are to get this value as a sum of two numbers here. And then for every value a here that is in the set, we look at this convolution at position 2a, and this will tell us the number of arithmetic progressions with a in the middle, and then we just sum them up. Just be careful, because a plus a is also 2a, so it's also going to count an arithmetic progression a. If you don't want that, you need to subtract it, but in general, yeah. Good. Another problem is just the generalization of this knapsack problem. But instead of uniting two knapsacks, let's assume that we're just solving knapsack. And when I say knapsack, again, I mean without weights. So we just have some weights, S1, S2, and so on, without value, yeah, only weights, Sn, and they sum up to S, big S. And I want for every value from 0 to S, to big S, know whether it's possible to achieve it as a sum of these items or not. This problem is called subset sum. Well, if you solve it stupidly, like a knapsack, you add an item to the knapsack one at a time. Your time complexity will be S times n, right? For every item, you go through your dp, you add something up, blah, blah, blah. But we can solve this faster. We will use this idea that if you have two knapsacks, you can combine them together. Let's just use divide and conquer. Let's take our items, S1, S2, and so on, Sm. Let's break them down in two halves. Let's recursively solve the problem for two halves. And then we can use FFT to combine two knapsacks into one big knapsack. If you do it stupidly, then it could be kind of bad, because on the last level you have n recursive calls, and in each recursive call you have like an array of size s. So this will be n times s. But note what we don't need to be up to s every time. If you have like a bunch of elements, there are sum of some subset is at most the sum of these elements, right? So if this is the second half, like n half plus 1, and so on Sn, this is the boundary that we care about. No higher sums are possible. So actually, if you do this, now everything works pretty fast, because on one level, in total, we have sum equal to s. So here, for example, we have sum equal to x, y, z, and x plus y plus z is s. And in every one of these recursive calls, everything we do is just, it's almost merge sort, time complexity, but we do fast Fourier transform. So this works in x log x, this works in y log y, this works in z log z, and so on. So in total, on one level, it works in time at most s log s. And because every time we split the number of elements in half, we have log n levels of this recursion. So this algorithm will work in time s log n, which could be much faster than s times n in general. Great, we solved knapsack. Also, you can solve integer multiplication. As I told you at the beginning, you just interpret digits of an integer as your coefficients of a polynomial, and you multiply them, and then you do some carrying. But you can do better, right? Because, well, we use integers with base 10. So your coefficients of a polynomial will be very small. It will be numbers from 0 to 9. And the size of your number is n, let's say. But you don't need to take base 10. You can take any base. Let's take base 10 to the k. This can be achieved by just blocking your digits by groups of k digits. This will be your first digit in base 10 to the k, second, and so on. And this way, the length of your number will be n over k. And then multiplying them will work in time n over k times log n over k, or log n, it doesn't matter. So you can save this factor k. But you should be careful, because at the end, how many digits you will have. So this number is up to 10 to the k. So we sum up, like n over k times digits up to 10 to the k times 10 to the k. So the resulting numbers could be something like n over k times 10 to 2k. And this should still be at most 10 to the 18. So it should still be in long. So for example, k something like 6 should work, right? Or 5, let's say 5 to be on the safe side, right? This would be 10 to the 10 times n is like 10 to the 6, so it would be 10 to 16. So this way you can speed up your number multiplication algorithm by the factor of k, so 5 times faster. The last problem we're going to talk about is how to use fast Fourier transform in dynamic programming algorithms. So the problem that we are interested in is calculating the number of binary trees of size n. So we want a binary tree that has n vertices, and every vertex can either have, like, it's a labeled tree. So the left child is different from the right child. So it can either have 2 children, it can have only 1 child on the left, it can have only 1 child on the right, or it can have 0 children. Well, this is easily solvable by dp. Let's take a root. There are some number of elements here, some number of elements here, right? So if this tree has depth h, let's calculate the number of trees with depth at most h, right? If you can calculate with at most h, you can take like dpnh minus dpnh minus 1, and you will get exactly h, right? So this is number of trees with depth at most h. This is at most h minus 1. Then exactly h is the difference. So this doesn't matter. Let's say depth at most h. So then, what do you have here? Here you have, for example, k vertices, and the depth is at most h minus 1, because here it was at most h. And here we have the rest of vertices, right? Here we have k vertices, 1 is the root, so the rest is n minus 1 minus k vertices, and the depth is also h minus 1. So we can write this kind of recursive, this kind of dp formula. dop of h and n is equal to sum over ok from 0 to n minus 1, dp h minus 1k times dp h minus 1 n minus k minus 1. And if you look at this formula, you can see that if we look at this dp as a level dp, so for example, we fix h and we increase h and we calculate for all n this value. Then the next level of recursion is basically just the convolution of the previous level of recursion with itself. Look here, like we sum over all pairs of indices such that they sum up to n minus 1. Not m, but n minus 1. So we do the convolution and then we shift it by one symbol, right? So to calculate the hth level of recursion, you just take the previous level of recursion and you square it. And this will take you like h levels, and on each level you work in n log n time. Just note that the number of trees is going to be very large, so probably you need to calculate this some modular, and you should take at every level of recursion the answer mod this number. And this modular should also be kind of small, right? Because if this value is at most modular, this value is at most modular, and you sum up n times, then your answer will be n times modular squared. If modulo is 10 to the 9, this is going to be too much. So probably your modulo should be something like 10 to the 5. It is possible to do fast Fourier transform mod some specific prime number. We're going to talk about that in the next episode. But for now, we just assume that the mod is small, and we can just take after it mod this value. This is everything I have for you today. This took us 3 hours. I did not expect that. I hope that it's going to be 2.5. But I hope that we learned a lot today. I tried to make this as simple as possible. I'm not sure I always was successful with that. I think that when we got to these roots of 1 on this circle, it was a little bit complicated. But I hope that if you rewatch this or come back to the notes or something like that, right? The notes will be available in the video description, and all the different sources that I used. Like, for example, there are some very nice videos and articles about complex numbers, and there are some interesting videos about fast Fourier transform. I can also share a video about how fast Fourier transform changed some of the parts of the world. Anyway, I hope you will find it interesting. And the most important thing, please solve problems. Please go to the contest that I provided or any other source you can find for problems on fast Fourier transform. And please solve problems. Please write the algorithm by yourself. Don't copy it from anywhere. If you need, come back here and relearn. I hope you enjoyed our stream today. This is everything I had for you today. If you have any questions, I will be happy to answer them. But other than that, I think we are done for today.